Welcome back to the Infinite Jungle.
I need to remind you to please refer to the disclaimer linked in the podcast show notes and note that none of the information in this podcast constitutes investment advice, an offer, recommendation, or solicitation by Galaxy Digital or any of its affiliates to buy or sell any securities.
On today's episode, I have with me Yiannis Psaras, the founder of ProbeLab. Very excited to speak with you, Yiannis.
Likewise, thanks for the invite and happy to be here.
I have talked about your analysis on ProbeLab's analysis before on the Infinite Jungle. But before we get into our discussion about the blob throughput increase for Ethereum, I thought it would be good to just get a quick rundown of ProbeLab as a company again. It's only through the ACD calls that I have learned about ProbeLab and kind of the amazing analysis and data that you guys gather. So Yiannis, give me an understanding of ProbeLab, why you started it, what it does, and how it's helping the Ethereum ecosystem.
Yeah, sure. So ProbeLab has started a few years ago, actually, initially as part of Protocol Labs, and it was focusing, our team was focusing on measurements and metrics for the IPFS network, the Filecoin network, and LipidP more in general. So that started a few years ago because it was very important to make sure that the networks that PL has been operating was running smoothly and they were as optimized as possible. Now, from then on, obviously, there are many LipidP-based networks out there, and therefore ProbeLab started looking into other LipidP-based networks. And of course, Ethereum is a big one, a big user of LipidP anyway. So we started looking into that. We started looking into other networks as well, so that we make sure that all of the kind of customers of LipidP, the users of LipidP, are doing as best as they can in terms of the networking protocols, the setup, the optimizations that can be done, and so on. So that's how we started a collaboration with the Ethereum Foundation and the Ethereum community more in general to look into several parts of the protocol stack. It's worth mentioning that our team has got lots of experience in Gossip Sub in particular, which is part of the LipidP stack, of course, but it's a very central and critical protocol for Ethereum as well. And that's why we got involved into this study that we're going to talk about.
That makes sense. And how long ago was the founding of ProbeLab?
I think it was around the beginning of 2022, maybe a little earlier. But at that point, it was part of Protocol Labs and then became an independent entity. Right now, we're with a broader entity called Interplanetary Shipyard, which is also housing the core developers of IPFS and LipidP itself. So we're in one team and kind of sharing resources and helping each other. But ProbeLab is more focusing on the metrics, measurements, and the tooling to make all that more efficient.
Gotcha. But I think that makes sense, the housing of ProbeLab in the IP. Did you call it the Interplanetary
Shipyard?
Interplanetary Shipyard, then the Protocol Labs. Yeah. So congrats on that. I want to focus this conversation on one specific study that you guys have done very recently, and I'm going to link to it for our listeners in the show notes of today's podcast. This study is titled Bandwidth Availability in Ethereum, Regional Differences and Network Impacts. And as it states in the introduction of the report, the motivation for doing this study is to find out what is the maximum target max blob count that the network can comfortably handle, especially for home stakers. So to set the stage, can you describe the methodology and the parameters of this study? How did you go about measuring the bandwidth availability of nodes, especially home stakers? And what were the most challenging aspects of setting up this study?
Definitely. So we, the blob count increase has been a hot topic in the Ethereum ecosystem, especially with the upcoming upgrade in a few months, and there is lots of demand from layer twos to have more capacity in the Ethereum network. So one very critical study was to see if nodes can transfer more blobs around the network. So increase the block count and therefore increase the block size as well. So what we wanted to do is try and figure out how much bandwidth, extra bandwidth nodes have got available compared to what they have today. Now, this is a challenging part because you can't really know how much bandwidth those nodes have got available. You have to set up the study such that you can saturate the bandwidth of other nodes, of the nodes that run in the Ethereum network, but at the same time do not disrupt, because these are mainnet nodes, so you don't want to basically attack the network trying to do a study for the good of the network. So we had to hit the right balance, and therefore for that reason we decided to, of course, not ask for arbitrary data out of nodes because they wouldn't respond anyway. So we decided to work with recent blocks that nodes have had anyway, and work with RPCs in order to try and request this data out of the nodes. So we've done some studies, as we explained in the post, and we figured out that the saturation of bandwidth was coming when we did 6 sequential RPC requests of 20 blocks per retry. So that means that what I mean by we figured out that this is the right balance is that we didn't see any more bandwidth being available if we increased these to 30 blocks per retry or 40 blocks or more than that. Instead, what we were seeing is less successful RPC requests. So the nodes would drop this because they had other more important things to do, and therefore they would not respond to our requests. So at that point, we thought it's not worth stressing the network and nodes more than they are today, and that's how we settled to that. And obviously, it's worth noting that for this study, we only could work with estimates because having the accurate bandwidth of nodes is not something that nodes are sharing. It's kind of confidential information, of course, and that should be totally respected.
You mentioned quite a bit of bandwidth usage on the upload side. Is there a large discrepancy between the upload bandwidth for downloads? There are some upgrades, I believe, that are happening for the peer-to-peer layer where developers have said on the calls that they've seen a noticeable difference between the bandwidth usage upload versus download. Wondering in your view, how that plays into the study.
We didn't actually have a very good way to focus on the downlink of nodes, but at the same time we kind of intentionally didn't kind of try too hard, if I can put it this way, because normally, especially in home connections, if there is asymmetric bandwidth, then it's the uplink that is slower. So you will very that's what is provided by ISPs, right? So if you are to get a lower bandwidth, this is the uplink. So we can assume that the downlink is always either equal or more than the uplink. So that's from the kind of line rate perspective. We didn't go further because, at the end of the day, it should be a kind of zero-sum game. Like a node should upload as much as it downloads. And therefore, we don't really expect huge differences there. Some differences might come when, peer sampling comes along, where the block proposer will have to sample and therefore will have to download itself lots of data from the network. And this it wouldn't be something that would happen continuously for a brief period of time while it proposes a block and needs to do some sampling. It will need to download lots of data. But again, I don't expect that this is going to be a problem compared to the uplink.
That's interesting. Like that discrepancy between the upload and download, it makes sense that it could get larger or smaller depending on the time within the slot that you're looking at. Because your study also shows that
Yeah,
most of the bandwidth usage is happening in the first 4 seconds of that slot. Um,
yeah,
One other question that I had about the study methodology and kind of the parameters that you used, one of the information that was shared about the study is that these bandwidth measurements are from roughly 9,000 nodes. And it says it's representing, I think this was a little bit of a typo in the report, but it says that it's representing 70,48% of total online reachable nodes. Is it 70%
yeah.
of total online nodes
So
that the study is measuring, or 48%?
it's 70%.
Okay, gotcha. Gotcha.
Yeah, yeah,
Yeah.
yeah. Yeah.
It, I,
I need to check the typo. Yeah,
no, that's fair. I was
if there
reading
is
it
one.
and I was like, oh, if I was like 70,48%. I was like, that, yeah, that definitely has to. Um,
No, it's 70.4,
gotcha.
70.48. Yeah,
Gotcha. No, that makes
yeah.
sense. I know in some countries, actually, a comma is a period. A couple of takeaways from the report that I found quite surprising and wanted to
Hmm.
kind of get some feedback from you on. The first one was the difference in bandwidth availability between cloud and non-cloud deployments being extremely marginal, only like 5 megabits per second. I thought that was a really
Hmm.
surprising difference because we're always talking about solo stakers putting running on very minimal hardware, perhaps with very limited bandwidth. Was that also a surprising finding to you? And do you think that that finding will materially change how developers think about solo stakers? It seems to suggest that solo stakers might actually have as much resources at their disposal as professional stakers.
Yeah, yeah. So it was a surprise for sure, to me at least. On the other hand, I would say that we should again take the results with a grain of salt, just because of the reason that when you have a node, the node is doing its duties to the network, so it's communicating with other clients through Gossip Sub, through the Gossip Sub protocol, and is exchanging blocks and everything else that needs attestations and everything. And then there is perhaps a little bit of bandwidth availability for RPC requests from other nodes, which is how we did our study. We didn't participate in the Gossip protocol itself, but we did RPC requests to the node. So this can happen in two ways. You can either think about it as nodes having a particular amount of bandwidth and then setting some bandwidth aside, perhaps like very simplistically for RPC requests, and this is what we have been measuring. Or, which is the second like explanation, which is a little bit more accurate, is that they're using as much bandwidth as they can, but then when there are RPC requests, they're trying to satisfy some of them as well. So they're kind of compressing the bandwidth that they have for like the gossip sub duties and the attestations and blocks and everything, and they're allocating some of the bandwidth to RPC requests. And that's how, that's the measurement that we did. Now, this is not necessarily representative of how much bandwidth they have available on the line, on the wire, but is more like, how much could you make available for this random guy that is asking you for something while you're still doing the rest of your duties to the network. Um, so that's a more kind of technically accurate way of seeing it, which is definitely interesting to see that the difference between solo stakers and kind of cloud hosted provide node operators is so small, in the order of 5 megabits per second. But I don't think we should conclude that either cloud-based nodes don't have too much bandwidth or home stakers have necessarily all the bandwidth that a cloud node could provide.
That's fair. Do you think even also the assumption that solo stakers are on the majority not using cloud hosted services, could that also be an assumption that may be a
Yeah,
bit weak.
it could be. It could be. That's one thing that we would like to dive more into and try to see, things related to how many nodes are behind a nut, for example, or these kinds of things. We haven't gone that deep yet, although we do have some data. It's coming down to some of the digging into the data that we already have to figure out more details about it. So the data analysis part.
I would say if there's a team that can do that kind of analysis and research, it's definitely your team. One other question that I had about this study is how it compares to some of the other studies that have been done related to the blob throughput increase discussion. ETH Panda Ops. The part of the Ethereum Foundation came out with a study to back up why a blob throughput increase to 6.9 is appropriate. That was the study that was primarily used to make the decision on the ACD call to move to 6.9. Tell me a little bit about what you thought about the study and how it compared to your study. Did you think that the study contained enough data and enough analysis to really make an informed decision?
Yeah, I think so. First of all, yeah, this is a great study by the ETH Panda Ops team. There's another also very interesting study by the Codex team that came out, I think, during the DevCon week, which also showed that there is, well, showed some numbers about bandwidth availability. It's worth noting that our study, at least the preliminary results, we shared in during the DevCon week with the Panda Ops and like other core developer teams. So it was not kind of the study like came out yesterday. We just wanted to rerun some experiments from more regions to make sure that our results are stable when we do and like we scale up the infrastructure. But initial results we had since before the DevCon week. And those were shared there in some of the conversations that we had. I think that the Panda Ops team did a great job, and they collected actually some data from solo stakers through their Zatu platform. And so the analysis that they did and the trend lines that they showed is a very kind of accurate and like nice study to look at. I would say that the two studies are kind of complementary to each other because none of the two says that the 6.9 block count increase is something that should not be done or contradicting each other or anything else. So I think both studies are worth reading, I would say.
Another takeaway from the study that I wanted to ask or dig a little bit deeper into with you on this show is you made a couple of recommendations on bandwidth saving improvements to Gossip Study and how
Yeah.
there are multiple changes that could be made that would significantly help nodes. You listed a couple. Some of them I recognized that have been talked about on the ACD calls. Others were completely new to me. Can you talk about the most effective one in that list from your view? Give us an overview of it, how easy it is to implement, and a little bit more detail on the one that you think from that list is the most effective.
Yeah, I don't know which one to pick. Maybe I'll pick the gossip diffusion, block diffusion topic, which is an issue in the consensus spec repository right now. Um, so the way that GossipSub operates is that it sends when a block producer is producing a new block, it shares it with its immediate group of peers, and then the same happens with every one of those peers. So that's how a message propagates in the network. Now, if you think that the network is a random mesh of nodes randomly connected with each other, you can kind of intuitively realize that as we reach like towards the end of the window of the propagation window, most nodes have received the data already. So I send it to my 8 peers. Each one of those 8 peers sends it to its own 8 peers, and each one of them do their own 8 peers. So there is a kind of diffusion effect that is going on through the like the beginning of the slot up to the fourth second, hopefully, and like by that point, all of the nodes in the network should have the data. Now, as you understand, when you reach like I don't know, say like hypothetically second 3 or 3.5, a lot of nodes in the network already have the data, and therefore what they're sending to their immediate peers is duplicate messages. So there is bandwidth that is used to propagate things that other nodes already have. So what needs to be done, well, one proposal that should be investigated is that in the beginning, when very few nodes in the network don't have the data, we should have kind of increased propagation velocity, but this velocity should go down as more nodes, as the message propagates to more nodes. So this is one of the proposals that have been discussed and is being put forward. I think it's going to reduce the number of duplicates a lot, and at the same time, and as a result, actually, is going to increase the bandwidth availability of nodes. So this is one of the proposals that is currently being discussed. I believe is not too difficult to implement, but there needs to be a little bit of kind of modeling as to how things can be done and implemented actually.
And the way that these types of changes to the gossip sub happen would this require a hard fork? Sometimes when it's networking related changes, I hear developers talk about implementing this asynchronously according to the whim of the client team. Is this also how the diffusion would be rolled out?
I think so. I think so. It's similar to the "I don't want" message that has recently, been included in the specs, and most like implementations now have it implemented. It has happened like kind of mid-flight. It has, of course, it has been tested previously, but yeah, I think it will not require a hard fork to get it in.
Now, there are a couple of hard fork related EIPs that have been recently touted as major improvements to bandwidth. One of them is EPBS, Enshrined Proposer Builder Separation, or as POTUS likes to call it, execution payload separation from consensus block or something like that. He mentioned that it would save bandwidth by orders of magnitude because it will separate out the very intensive the intensive computation required in the first 4 seconds of the slot. Do you have any thoughts to share about the bandwidth savings for EPBS? I noticed that it wasn't included on the list, so I wondered if that was intentional.
Yeah, I don't know if it was intentional or not. I do believe that it is going to save bandwidth, but I believe there have been discussed some kind of downsides to it as well. Like, you kind of delegate responsibility to other nodes, and therefore maybe this has to be looked at not necessarily so much from the technical perspective. Well, both from the technical and non-technical perspective. So. I do believe it's going to save bandwidth for some nodes. Again, overall, as we said, it's kind of a zero-sum game from the point of view that as much data needs to be uploaded and downloaded, it will have to be done so. If some nodes take a larger portion of it, then of course that kind of changes the balance between nodes. But at the end of the day, it's the same bandwidth. Now, for this, I think there are some benefits to the CIP though.
Yeah. One final question that I had related to another takeaway from the study was related to the geographical distribution of nodes. Your study states that 65% of nodes are in Europe or the US, and that these nodes have more bandwidth availability than the nodes that are located more remotely. I think particularly it was Australia that was mentioned, possibly.
Yeah.
To what extent do you think that because of the P2P architecture and the natural incentive to co-locate in areas where there are more nodes for better performance reasons, to what extent is that a centralization risk to Ethereum that needs to be addressed?
Yeah. Yeah, very good question. So, first of all, to clarify, it's not that like the node in Australia or nodes or uh, connections in Australia are lower bandwidth.
Mm,
It's just because they are further away, you cannot. The latency is such that makes the entire data transfer a little slower. So generally, bandwidth is one thing, but latency is also another thing. So what is frequently being used in networking terms is the bandwidth delay product. So it's not only the bandwidth but the delay, and the faster, the lower the delay, then the faster that basically the transfer becomes. Now, and this is why we've seen some discrepant, like lower bandwidth availability to remote areas such as Australia, which was just one of the deployments that we did for this study. Yeah, just to clarify that there's no problem with running a node in Australia
mm.
or Australian, I don't know, ISPs or anything, or anything like that. It's just that the delay to get there is too big.
Gotcha. It's not like they have like
Now,
lower grade tech or hardware or
no,
anything like that. It's the way that the latency happens. It indicates that things
exactly.
yeah, okay, that makes sense.
Exactly. Yeah, I haven't checked, but I'm pretty sure they have okay, very good bandwidth and connectivity and everything. So it's the delay that plays a role. Now, in terms of centralization, this, like what you mentioned, exists, and if I guess you have been to our website on ProbeLab.io, there is a distribution that shows exactly how much is in the US and in other European countries and like other countries all over the world. Um, Now, I wouldn't say it's like a risk, a real risk, because it's quite a big footprint anyway to have the whole of Europe and the whole of the US, like running the majority of the network. I don't think it's a problem per se, but I think the network would be healthier if there was more distribution and nodes like in other areas as well. To what extent this plays a role in the block propagation through the gossip sub protocol and so on, again, is difficult to say. We would need very fine-grained measurements. But one optimization kind of direction that we have, which we haven't yet discussed at all, actually, but we plan to do so soon, is to, as Gossip Sub builds the mesh of nodes for each individual node, basically, what should happen is that each node should choose a range of latencies to other nodes. So it shouldn't be that a node connects only to nodes that are very close together with it, but reject some of those connections in favor for RTTs that would go to 200 milliseconds, 500 milliseconds, or more, so that every node is connected with a variety of other nodes, and therefore the diversity of geolocation comes naturally into the very bottom of the network stack. So I think that logically makes sense, but we're still to hear feedback from others.
I would imagine that also as a counterweight, the anti-correlation penalties that exist on the consensus layer to penalize in the case of a slashing event also may help to some extent. Although, again, I think that's really more for like one data center rather than like geographic diversity across like continents, which is really what we're talking about here. And the co-location between builders and relays and validators are have a little bit of a different incentive dynamic. So yeah, interesting, very interesting things. Thank you so much, Yiannis, for chatting with me about the study. I've wanted to have you on the pod for so long. We've discussed this for months, even before DEF CON.
Exactly, months ago. Yeah. It's great chatting with you. Thanks for the very interesting set of questions. Really, really thoughtful.
My pleasure. And thank you for being so thoughtful about wearing something jungle themed to our show. That is our theme, the infinite jungle that is Ethereum. I love your short. And thank you to our listeners for tuning in for another episode of The Infinite Jungle. We hope that you learned something new about Ethereum. I am signing off from the concrete jungle that is New York City. Yiannis, where are you signing off from?
I'm in Europe, in Athens, in Greece.
Cool. In Greece. That's awesome.
Yeah.
So we are signing off from Europe and the US. And I hope that you'll join again for another episode of the Infinite Jungle. In your explorations of the infinite jungle that is Ethereum, stay safe out there.